When a building reaches over half a mile into the sky, it raises an immediate question. How do millions of tons of glass and steel resist the constant downward pull of gravity and lateral wind forces without tipping over? Tensile strength and forged steel provide the raw material for these heights, but the logic keeping them suspended in the air is defined by ancient geometric laws. Specifically, 3 mathematical rules governing proportion, angles, and curves provide the necessary framework for physical stability. These rules often appear as dry proofs on the flat pages of a high school geometry textbook. Yet out in the physical world, these same equations dictate whether a 3-dimensional structure stands tall or collapses. Mathematics is the unyielding blueprint of reality. Architects who follow these formulas achieve balance. Those who deviate face the immediate consequences of gravity. The first rule focuses on the triangle, utilizing a principle of basic proportionality to manage and distribute massive, unequal loads. Take a standard triangle. If a line cuts across it perfectly parallel to the base, it divides the 2 outer sides into the exact same ratio. Regardless of where that parallel line is placed, the ratio of the side segments remains identical. Because these proportions are locked, structural stress is distributed predictably across the shape, ensuring one side doesn't experience more strain than the other. Engineers scale this ratio to create structural trusses. By interlocking triangles that divide space proportionally, they can take a concentrated weight at the top of a structure and disperse it evenly down to a wide base. The construction of the Eiffel Tower relied entirely on this geometric scaling. These interwoven iron struts use proportional division to manage the immense, shifting weight of the metal above them. Without this mathematical guarantee of proportional division, weight would concentrate at individual joints, causing the ironwork to snap under its own mass. The second rule establishes the absolute law of the right angle, commonly known as the Pythagorean theorem. If you build a square off the longest side of a right-angled triangle, the hypotenuse, its area matches the combined area of the squares built off the 2 shorter sides. The converse of this rule is what makes construction possible. If 3 structural beams satisfy this equation, the angle between the 2 shorter beams is physically locked at exactly 90 degrees. This 90-degree lock is a structural requirement. To transfer gravity directly into the foundation, vertical pillars and load-bearing walls must stand entirely perpendicular to the ground. If a frame shifts from 90 degrees to even 85 degrees, the downward force of gravity becomes a lateral force. The beams lose the ability to transfer weight straight down, leading to total collapse. Every plumb line and skyscraper column is a physical application of Pythagoras' theorem, ensuring gravity travels safely into the earth. The third rule governs the hidden geometry of curves, specifically how circles interact with straight lines, or tangents, to create suspension structures. When 2 straight tangent lines are drawn from a single point to touch the outer edge of a circle, those 2 lines are always identical in length. Furthermore, a line drawn from the center of the circle to the point where the tangent touches creates a flawless 90-degree angle. This combination of equal lengths and perpendicularity allows for the engineering of massive suspension bridges. The vertical cables act as tangents to the arc of the main cable, creating symmetric tension across the span. The sweeping curves of modern infrastructure span vast distances because these tangent rules maintain a state of absolute structural equilibrium. Proportionality, Pythagoras, and tangents function as a combined force for managing physical mass. Long before these theorems were formalized in textbooks, builders utilized these geometric ratios to stack millions of tons of limestone into enduring monuments. While building technologies change, the geometry remains static. It is the language that dictates what can be physically realized and what will succumb to gravity. The proofs found in geometry textbooks are the blueprints for the structures around us. Mastering these rules offers a way to decode the built environment. Hit subscribe to continue exploring the hidden rules of reality, and I'll see you in the next one.